As indicated by the title, the main purpose of this video is to differentiate between the sliding motion and the rolling motion. Along the way, we are going to try to understand what causes objects to roll. As an example, we are going to use a block which is shaped in such a way that can only slide, and the rolling object is going to be a uniform solid disk. Notice if the two objects are placed on a frictionless surface, their motions are going to be identical. That motion is going to be a sliding motion, and the two objects are going to have the same acceleration. The solid disk, and that's true for all rolling objects, cannot roll unless there is a static friction that trips them and causes them to roll as indicated by the animation. Notice also that this static friction does not take energy away from the disk. Instead, it helps it to roll only. As a result, the kinetic energy of the disk is split between translational and rotational, but the total kinetic energy at any point in space is the same as the sliding block. This is due to the fact that the total mechanical energy of the system is conserved. Now, let's detail mathematically the motion of the two objects and compare their speeds as they travel down the incline. The sliding block is clearly under two forces only: the normal force, which is perpendicular to the surface of contact at all times, and the weight mg, which acts straight down. The work done by the normal force is equal to 0, because the normal force is at all times perpendicular to the displacement, and since the normal force is the only non-conservative force that is acting on the block, therefore the work done by the non-conservative forces equal to 0. This conclusion allows us to use the conservation of energy principle, where the kinetic energy initial plus the potential energy initial equals the kinetic energy final plus the potential energy final. The kinetic energy of the block at the top of the incline, which is the initial position, is going to be 0 because the object is released from rest. The potential energy is in the form of gravitational potential energy, which equals mgh initial. That equals the kinetic energy final, which is 1/2 mv final squared, plus 0 potential energy at the bottom of the incline, because we are going to use the bottom of the incline to be the reference point of measurement for our heights. Notice that the mass is a common factor, therefore it cancels out. This equation can be simplified further, where gh initial is going to equal 1/2 v final squared. Solving for the v final, we obtain square root of 2 times gh initial. In the case of the solid disk, there are 3 forces acting on it: the normal force, which is acting perpendicular to the surface of contact; the weight mg is acting straight down; and the static friction force is acting up the incline and parallel to the surface of contact. As we know, the work done by the normal force is equal to 0, because the normal force is perpendicular to the displacement at all times. The work done by the static friction force, as stated earlier, is always going to equal to 0. Therefore, the work done by the non-conservative forces is going to equal to 0. This conclusion, again, allows us to use the principle of conservation of energy, where the kinetic energy initial plus the potential energy initial equals the kinetic energy final plus the potential energy final. The solid disk is released from rest at the top of the incline, therefore its kinetic energy initial is going to be 0. Its potential energy is mgh initial. The kinetic energy final at the bottom of the incline is in two forms: translational, which is 1/2 mv final squared, plus rotational, which is 1/2 I omega final squared. The potential energy at the bottom of the incline is going to be 0 because we are going to use the bottom of the incline as our reference point of measurement for the heights. Now let's simplify this equation by substituting both I and omega by their respective expressions. The equation is going to be mgh initial is going to equal 1/2 mv final squared plus 1/2 times I, which is the moment of inertia of the uniform disk, which equals 1/2 mr squared, times the angular velocity squared, which equals v final squared over r squared. Notice that the r squared are going to cancel out. The mass is a common factor, therefore it cancels out also. And this expression can be simplified further, where gh initial is going to equal 1/2 times the v final squared plus 1/2 times 1/2, that's 1/4, v final squared. This expression can be simplified further, where g times h initial equals 3/4 v final squared. Isolating the speed v final, we obtain square root of 4/3 gh initial. And clearly the speed of the uniform solid disk is less than the speed of the sliding block, which was found earlier to equal square root of 2gh initial. This is due to the fact that the kinetic energy of the disk is split into two different forms, translational and rotational kinetic energies.